Is mic on? Oops. Yes? All right, let's get underway. So we're still grading exam 3 and homework 2. Exam 3, I'm pretty confident we'll have done by Monday, so that'll be out, and you can, we'll discuss the solutions to exam 3 on Monday when you have your grades. Question of day 16 really is out. It's already up, though I think it's not released until 11. And it's fairly simple. It's a regular expression that you have to write. It's a little bit of tricky stuff to it to get it to pass the test cases, but nothing too bad. The regular expression itself really only uses what we have done in class on regular expressions. Now I have assigned a reading from the Python for Everyone book, which has a chapter on regular expressions. I think Python does not. So you should go read the regular expression chapter in Python for Everyone. And again, focus on the simple things and the concepts, not so much on the fancy stuff that they do. And we'll probably finish regular expressions today. There'll be 2 more question of the days next week, and that'll be it. We only have 2 more weeks of classes, so there won't be any questions of the day the last week of classes. So that means there will be 18 of these, and I think we drop, I don't remember what the syllabus says, 30% would be we drop 6, something like that. You'll have lab 11 next week, followed by 1 more lab the final week of classes, so 2 more labs. Be lab 12. Again, I forget how many we're dropping of these, but it's in the syllabus. Homework 3 will come out on Monday, and will be due on May 6th, last day of classes. This is a text processing kind of problem like we're doing now, so everything that we've done now will be germane. It will be object-oriented, so that you can reinforce some of the object-oriented concepts we talked about with the Barbell implementation and with exam 3 in the previous lab. And somebody asked about the final exam on Piazza. This is our assigned time. We don't actually get to pick final exam times. Final exams are assigned by the university based on your schedules. So the large multi-section classes like this one tend to be at the end of the exam week. So exam week is actually the last slot in exam week, which is Friday the 13th from 3 to 5. The fact that it's a Friday the 13th, wow, this is a cool pointer. The fact that it's Friday the 13th, I don't know if I should worry about that or not, but there it is. And then you'll be done. So let's get back to what we were doing. So let's review briefly what these regular expressions are and how they work. So you recall that we talked about 2 different regular expression functions, match and search. The fact that they have an RE first. How did that work? There we go. Yeah, it doesn't work that well. Come on. Okay, the fact that there's an RE is because this is from the regular expression library, so that's the library or module.function name. For RE match, what you do is, okay, I'm not pressing the button now. I hate it when I forget my clicker. Okay, so for RE match, the first argument is the pattern, so that any extra special characters like the asterisk in this case will be interpreted in the pattern. The second argument is the target string. So this is asking find anything with A and then 0 or more B's in the match object. And we see that it starts, because it's the match expression, it starts matching right at the beginning of the string. So if the first letter of the string, of the target string, were not A, this would fail immediately and just give up. So here we find AB star, right? We find that there's a match object from 0 to 2, so in the 0th location of the string, up to not including the second location, and it tells us what the match is. The value returned is an object. It has instance variables that are things like match. So you can say x equals RE.match and then ask for x.match, and you'll get back the string that matched. In the case of RE match CA star, I'm missing a prompt. This returns none, because there is no instance of CA in that starting at the beginning of that string. So it fails. There's no match. But if I do this with RE search instead of RE match, it will keep searching the string until it finds a match, and it will return the span of the match from 2 to 4 and the match. So you'll notice that in RE match, the span always starts at 0. If there's a successful match, it always starts in location 0, by definition. With RE search, it starts searching at location 0. It'll return the first successful match it finds, starting anywhere in the target string. That's the big difference. All right? And because the match in RE search is sort of fluid in the target string, we have two special meta characters, caret and $, which anchor this to the end of line and beginning of line. So if you have a new line in there, you can anchor things to it with a $, or a caret, depending on which side of the new line character you're on. All right, caret is also the beginning of the first line. $, is also the end of the target string, the end of the last line. Questions? So we're all on the same page, right? So let's go on with some more stuff. I had told you on the other day in class that a regular expression is kind of like a little program written in its own little language, right? And we know about writing programs. We often compile programs because they run more efficiently. If we don't compile the program, we're interpreting the program, which means there's another piece of code or software called an interpreter that's looking at that pattern and navigating through the string in accordance with the pattern. And that's how regular expressions work. But I can make them much faster if I take the regular expression and build it and compile it to get a specific machine language version of the matching process for that regular expression. And in Python, I do that with the compile method, or compile function from regular expression module. This returns an object. So I'm going to take this regular expression, which we've seen before as a phone number expression. And what I'm going to do with it is I'm going to compile it to get something, which I called P, which if I look at it is an object, is itself it's actually a function that's been compiled and built, like a custom function for this regular expression. So when I call RECompile with a regular expression, I get back something that looks like this. Think of it as a special function, like a lambda expression almost, that just matches that regular expression. If I take this matching object, this special function, which I called P, and I invoke its match method on a target string, the value that I get returned will be the match object for that compiled expression. Now this actually, if you think about it, makes sense. The compiled object is the compiled regular expression is really an object with methods. The methods it has are things like match and search. And when you call match with a target string, self is the regular expression in its compiled form, and the argument is the target string. When you call self.search on the compiled object, self is the compiled matching function object, and the argument is the target string as well. If I try to try match here with the same pattern, notice that once I've compiled the pattern, I can use it as many times as I want. So I can call p.match on a different string, and this actually will return none. Why? Because I'm using the match method, which starts searching at the beginning of the string. And the pattern I compiled up there doesn't match this. Doesn't match it because it starts looking for a left parentheses. So that fails and returns none. On the other hand, oh geez, what happened? Man, this thing is touchy. It skipped a whole page ahead. What the heck? Right. On the other hand, if I were to use the search method on this compiled expression with the same target string starting at this will actually match. Come on. Will actually match, and will return the match object starting in character 8 through 22 and the match string that it found. All right? So what have we seen? We've seen this kind of match function that takes a regular expression and a target string. The search function takes a regular expression and a target string. the compile function which returns a regular expression object with a similar match and search method for searching, and the fact that I compile that string, that regular expression into an object, makes it much more efficient. So I can do very fast regular expression searches if I'm searching for the same thing over and over again. Okay, so that's half the battle. And when I get a match, because I have the spanning elements and because I have the match field, I can actually find out which part of the target string is the match. Right? I can just say, give me the phone number you found in there, and it'll tell me what it is. But there are all sorts of other objects or other methods that I can use to find out what match. So here's an example. I'm using the match function to match my usual regular expression against a phone number, or a social security number in this case. I get back the match object, and I can ask for the start. I can use the start method of that match object to get back the initial index into the target string. I can use the end method of the match object to get back one, sort of the end index, 1 over the last character of the matching element of the target string. I can ask for the span, and I'll get a tuple back, which is what we see in the printed representation. And I can ask for the string, which gives me that match string over there. And if I ask simply for RE, right? If I ask simply for m.re, m is my match, right? M is the thing that I got back, the match object I got back. I found out that that match object is actually the compiled version of my regular expression. So the hidden thing that's going on here is you can build a regular expression and compile it and then use it repeatedly, or you can just invoke match and search, and it will secretly compile it before it runs it anyway. And then you can just continuously reuse that returning match object. Okay, sometimes I want to do repeating qualifiers. So what does that mean? Well, in this case, we've seen the asterisk before, and it applies to the preceding pattern element. So the example you saw was AB star, and that matched a string that starts with an A and has as many B's, 0 or more B's. But I can actually use the left and right parentheses meta characters. Now here, notice that here the left and right parentheses don't have backslashes. That means that their special meaning is intact. And the special meaning of the left and right parentheses in a regular expression is for grouping. So it says these pattern elements, in this case A and B, they actually go together. So when I have an asterisk after the pattern element, the asterisk now doesn't pertain to the B, but pertains to AB together. So this is saying, look for the subpattern AB and see how many times you can match that. So in fact, I have a span from 0 to 10, and you'll notice that it matched the whole string, even because the pattern here, AB, is not matched, is matched as a group, right? So it's AB, 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 right? Everybody sees that? So the grouping characters, left and right parentheses, can be used to make a subpattern to which you can apply all the other constructs we've talked about. Plus, question mark, asterisk, the curly bracket repeats. So we can build more sophisticated patterns by grouping. In addition to, okay, so let's look at an example. So this is an email address. An email address can start with a digit. So you probably know this from creating your own like Gmail accounts and stuff. You cannot have an email address that starts with 1 or with a digit. It has to start with a letter. It must contain an @ sign to separate the name, login name from the host. And it must end with a 2 to 4 letter only domain. So for us it's .edu, .com, .it, you name it. It can't be .itxy. It's got to, it can't be .itxyz. It's got to be 2 to 4 letters long. So how do we express this? Well, this is my regular expression for an email address. Now you look at this and you go, oh my goodness, this is so obtuse. But it's actually really magical when you understand it. So let's walk through this expression and figure out what it means. So you'll notice that it's anchored with a caret at the beginning and a $sign at the end, that means that I'm trying to match the whole string. If you don't consume the whole string, it's not a match. So you want, when I use re.match, I don't want to match the beginning of a string and say that's an email address. I want to match the whole thing or not match at all. And we'll look at the start, we'll notice that there's an ampersand right in the middle, and that character is not quoted in any way. It is not a regular expression matching character. It's a verbatim @ sign. So just looking at this pattern, I know to the left of the @ sign is the email login name. To the right is the host name, right? Like my email address is vinci.cs.uio.edu. So let's look at this here, the host name part first. In the host name, we have any number of characters. This first bracketed expression says a class of characters that are either \w or word characters. Right, so we've seen \d for digits. These are for alphanumeric characters, for alpha characters. So the first thing here says I have either a word character or an underscore or a hyphen. All of those characters are legal. I have one or more copies of them. So that's the first part of the host name. In my address, it matches Vinci. Then we notice that there are one or more of them because the plus sign says one or more of them. So it's at least one letter long host name. The next part of the expression in the grouping characters has an explicit period. Remember, period is a special character. But if I backslash it, then it loses its special meaning. It's just a verbatim period. So this grouped expression, which is exactly like the first part, but with a period, says you have a part of a name followed by 0 or more, that's the asterisk, 0 or more repeats of that separated by periods. Right? So you have a word, and then you have dot word, dot word, dot word, as many of those as you want, from 0 to as many as you want. That's the rest of the host name pattern. Followed by, and this is its, shoot. Well, that doesn't work. Come on. All right, let's do this. So this we already said was like a word, 0 or more or 1 or more characters. That's what the plus means. Then I have a grouping of exactly the same pattern, 1 or more characters preceded by an explicit dot. So it's like vinci.cs.uiowa, and then that subpattern is repeated 0 or more times, and then I have an explicit dot with A through Z and A through Z between 2 and 4 times. So that matches .edu, it matches .com, matches .it, and so on. So we can see that this part of the expression, does everybody see this? Is like hostname, 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 .edu or something. Preceded by the @ sign, and the only thing we have left is this part. Well, this part looks exactly like here. We have that same sort of pattern, the \w character, underscore, or hyphen, which can be used in email addresses. And we're going to have a real email, which starts only with the alpha characters, but can have numbers in it. So W is just like this character class, but adds digits. So A through Z, A through Z, with a number which just cannot be the first character, repeated as many times as I want. I can have as many periods of the email address as I want, followed by alphanumeric stuff, 1 or more times, asterisk, 0 or more times. So this is my email address matching function. Wow, it looks dense. Regular expressions can be really complicated. It is rarely the kind of thing you write right the first time. There are a number of websites where you can go and practice your regular expressions. You're writing some code, you want to write a regular expression, go to the regular expression checker online, type your regular expression and a few examples to make sure you have it working. Because it's really hard to get this right. It takes a lot of practice. This is not a regular CS1 skill. Advanced regular expressions are like CS, algorithms level skills. You'll get there. So let's review. A through Z with the caret says the first letter is not a digit. The next expression, the backslash W minus, this part here extends that first letter to additional alphanumeric underscore or minus characters. Then the asterisk here allows optional period separated elements. So my Gmail address has alberto.segre. The dot actually is allowed explicitly in email expressions. And this will match all the legal email addresses that you expect. All of these addresses would match just fine. Now, REmatch and REsearch have a bunch of optional arguments, some of which can help you debug your regular expressions, and they're also meaningful because they let us see how regular expressions work. So for example, I know that this REmatch does not match because I'm looking for a lowercase ab and my string starts with an uppercase ab. But if I add the optional argument reignore case, this is just a constant, it's like a value, like true or false, then it matches. It says, hey, AB star matches the first ABB in ABBA because it's ignoring case. So you can get your regular expressions to ignore case. They're generally case sensitive, but you can turn that off. You can also use, remember this caret here in Python. This is the bitwise and, or bitwise or, bitwise and, that combines these two values. And we'll notice that when I turn on debugging, I actually see the trace of how my expression matched. This first thing I found is literal 97. Well, A is actually 97 in the ASCII character set. And it says, I'm looking for an A, then I'm looking for a 98, which is B, but I'm going to let it repeat between 0 and this many times. This is an internal limit. And then it returns my match. So if your regular expression dies and you can't figure it out, you can turn on re.debug and you see the whole matching process, which can be extremely verbose. But within a pinch, this is a valuable way to debug. So if I have more complicated patterns, the debugging information gets worse. So for example, new regular expression matching construct find all. Find all asks me to find all versions of AB star in this pattern with case ignored. So let's just look at it, forget about the answer there. It's clear there's what an AB. Find all works like search, so it looks in the rest of the string, and it notices ABBB is a version of AB, uppercase, and then the last AB is a version of AB. This find all returns a list of matches. And the matches are shown in the list that it returns. I can even iterate over matches, which is what Kyle asked for last time. He's not here today, but this was a question he asked last time. I can say for every match in find iterative here, I could just print match and it shows me, here are all the matches. 1, 2, 3. Just prints them out for me. So you can do iteration over matches. This is the way you probably use find when you're writing a paper looking for all, typographical errors of the same type, for example. We've used string replacement before. Regular expressions have their own substitution mechanism, which is more powerful because you can replace patterns with instantiations of those patterns. So let's take a look at a substitution with a regular expression. So here I'm going to say for every instance of the AB star pattern in that target string, this is in the search sense, so all instances, replace that with the character X, and you can see the result. So string replacement, which we've talked about in the past and you've all used, string replacement is sort of the beginner's version of replacement. Regular expression replacement is the full toolkit version of string replacement. You have complete control over how and what you want to replace. I can even limit the number of replacements by number. I can provide an optional argument that says replace the first version of AB with the letter X. I can say replace one version of the letter AB with the the X. I can supply the ignore case argument, which will recognize all versions of AB, including the uppercase ABB, and replace that with X. And I can say, replace the first two versions of AB with ignore case, and you'll notice that the third version is left intact. I can even say, substitute with the n, so sub n says, not only do the substitution, but tell me how many times you substituted. Those of you whose Word will recognize this from the little find and replace box, when you type in a find and replace item, it says 17 versions replaced. There's the primitive that lets you do that. You know, with regular expressions, it's like the gift that keeps on giving. There's always a new meta character, always another feature that you didn't know you needed until you find it, and then realize that there are situations where this is exactly the right thing to use. So let's take a look at what they might be. In our previous matching with search, I told you about the caret and the dollar meta characters, and I told you caret matches the beginning of the target string and dollar matches the end of the target string. But actually it's a little bit more complicated than that, because sometimes the string, the target string, has actually multiple lines in it. We've been doing these matches in class on short strings, but imagine now that that string is actually the text of the book Moby Dick, right? Huge string with the whole text of the book. The caret and the dollar sign actually represent the beginning of a line, which is the first character or any character following a new line. And the dollar sign matches the end of the line, which is the last character of the string or any character immediately before a new line. So those are our meta characters actually have multiple interpretations when there are many lines in the string. If I really mean beginning or end of string instead of beginning or end of line, then I should use \A and \Z to match exactly the first and last character of the string only. It ignores multi-lines. What about \B? Well, \B is a special meta character that matches a word boundary. If you think of a character string as a sequences of words separated by punctuation or white space or any other character that we don't normally associate with the word, that \B matches that boundary. It doesn't actually match any character. It matches the boundary between characters. And \B, it matches not a word boundary. So it's the opposite of \B. And finally, the pipe, this is called a pipe character, is used for pattern alternatives. It stands for OR. So let's see some examples. So here's a regular expression substitution that says substitute the pattern ABC or DEF with the string X. And as I look at the target string, I have an ABC here, and I have a DEF there, and an ABC there, and all of these are replaced with X. So it's not looking for it's looking at the same time for two different strings separated by the pipe. So match this or this and replace it with X. Also, this pipe character has the lowest precedence when expressing regular expressions, so that its default meaning is this and not this, which would be the alternative if it were a high precedence binding character. The first interpretation is the more natural one anyway, so you probably would not have this problem, but sometimes people get stuck on the use of the multi-line of the alternatives pipe character. Let's do some more grouping. So up to now, we've used grouping to take pattern elements, put them together, and apply pattern modifiers to those elements as a chunk. Remember the grouping of AB with an asterisk. We have now defined a new subpattern. But we can also use grouping characters to say, match this pattern, and then I can refer back to elements by parentheses saying, what subpattern did that part of the pattern actually match? This is best described by an example. Really, up to now, we've only worried about the entirety of the match. What was the phone number you found? What was the social security number you found? If I'm really after something where I say, what's the area code in the phone number you find, I need to be able to extract that from the match in an interesting way. So here's my same example from before. And all of the stuff we've seen before, the span is from 0 to 10. And I ask for the grouping, it tells me that it's AB, AB is a whole match. But if I say, what is the grouping 0, this index here tells me what is contained in the 0th, in this case first, parentheses set in the regular expression. So go back to the regular expression, there's only one parentheses set. It happens to be the entirety of the match. So group 0 is the string that matches whatever is in that first set of parentheses. That seems silly. It seems just like the regular grouping. But in fact, if you have multiple grouping parentheses, it lets you isolate parts of it. So let's try again. Here's a more explicit grouping. It says match A, B, C, D. There are no pattern modifiers here, just grouping parentheses. And when I have a bunch of grouping parentheses in a regular expression, they each have an implicit index. The first grouping, the second grouping, the third grouping, and so on. And the way to know which index is which is you scan the pattern and you assign a number to left parentheses starting from 0. So the first grouping, group 0 here, is the one that binds from A to C. That's grouping 0. The second grouping is the B grouping. All right? So let's match this. It's clearly going to match. The group result here is going to be the entirety of the match. But if I ask for group 1, I will get back ABC. If I ask for group 2, I'll get back just B. If I ask for all the groups, I'll get a tuple of the groups that were found, the subpatterns that were found in the regular expression match. I can even say, give me a pattern of subgroups, 2, 1, 2, and I'll get all of them back repeated if necessary. So the trick to remember is to get those numbers, scan left to right and label the left parentheses in increasing order to get the match. And we start here at 1 because group 0 is the same as the group without the argument. So the default argument for m.group is to give it a 0, which says give me the whole match. Yes?
If the letter D in the first parameter is not part of the first group, then what is it part of any group at all?
If the letter D, sorry?
If the letter D in the first parameter is not part of group 1?
Yes, it's not. It's not part of group 1, but it is part of group 0, which is the entirety of the match. Right? In fact, when I don't give an argument in the first expression there, that's essentially the default argument is 0. That's the entirety of the match, and you notice the D is there. But when I ask for group 1, I only get the part within the first parentheses, which is the first parentheses I find from the left plus its matching parent up to the matching parent. Okay, now we're going to get to this today, I hope. There is a way to write a pattern such that you can refer to which group number inside the pattern. In other words, let's say I have a pattern of characters that has one group with parentheses here. In my pattern, I can put another grouping here that says, whatever this is, make it the same as group 1. So that it is constrained to match only what I find before in the pattern. And I'll show you an example of this in a minute. That's one of the important features of grouping, is it lets me write patterns that refer to parts of themselves. So you should be thinking, this reminds me of recursion, which it probably should. So these are, like I said, regular expressions are their own little language. It's like writing a new program in a programming language just for string matching. Okay, we've seen backslashes in strings. We've seen the use of backslashes to introduce special characters like new lines or tabs. We've seen the use of backslashes to remove special meaning from special characters, like backslash backslash matching just a regular backslash. We've certainly seen backslashes in character classes like backslash D, which says this is not the letter D, it's a class of numbers, the digits. We've seen backslash W, we've seen backslash S, and so on. We can use, we've seen backslashes to escape meta characters. We know the left parentheses is the grouping meta character. But in our phone number example, we had backslash left parentheses that said, this backslash, this parentheses is really just an explicit verbatim parentheses. So backslashes giveth special meaning, but they also take it away. So it's contextual. Backslashes can be really confusing. It can escape its own meaning. Backslash backslash says, this is no longer an escape character, it's just a backslash. And it can be used inside a character class, like to take away the special spanning meaning of the minus, or outside the character class, like to take away the repeating meaning of asterisk in a regular expression. But here's the kicker. Backslash is also the Python escape character. So when I'm writing a regular expression that has a backslash in it for the regular expression, I need to tell Python that Python should not interpret that backslash. It should leave it for the regular expression. So we get this unfortunate situation where in a regular expression, every backslash that's supposed to act like a backslash may require its own backslash as well. Okay, so here's how to think about it. Okay, sorry, let's get a regular expression example. Okay, so let's say I want to match a pattern that is digit, digit, digit. I want to write this pattern. But the pattern itself, when I pass it to my REMatch function, is a string. So I want the D's not to be interpreted by the Python string mechanism as something with a backslash. I want that backslash to be evaluated by the regular expression. I want to delay evaluation of the backslash from the string mechanism to the regular expression mechanism. So to ensure the explicit meaning of backslash to the pattern matching engine, when I pass this string to the regular expression match, I need to escape those backslashes so that when Python reads the string, it doesn't try to interpret the backslash. So once the string is interpreted and passed to the pattern matching engine, the leading backslashes are all consumed because Python will see backslash, backslash, and say, oh, that's just a backslash, and the meaning it gives the pattern matching engine will be the desired meaning of the backslash D. But if I want to avoid the meaning, I have to escape the backslash twice, each one. And so each backslash now becomes two backslashes. All of a sudden I got four backslashes. And if you've noticed errors in my slide, it's because my typesetting system for my slides also has backslash escape characters. So I have some slides, if you look at the source, where every backslash has become 8 backslashes. It's a nightmare to keep it straight, and that's sometimes why characters get transcribed incorrectly. So let's look at some examples to help make this clear. To search for a backslash D in a regular expression, I need to produce patterns which contain, to search for explicit backslash D in a pattern, I need to produce a pattern which contains backslash backslash D. And to do that, it's itself a string that's going to be represented as escaped version of each backslash D. So if I want to literally search for these two characters in my text file, the regular expression target search expression is this. To get this in a Python string, I have to write this, and I'm off to the races with backslashes. There has to be a better way. So let's see what we got here. So I have a target string, which is a Python string. So this Python string is actually backslash D, backslash D, backslash D. It's actually 6 characters long. This is the way I have to input it. My matching string is, 3 of these like this. And I do find a match, and you'll notice that the match is, even though it's represented as 9 characters, is really only 6 characters long, because these explicit backslashes here are escapes to the meaning of backslash, the escape character. So this gets to be really kind of not just messy, confusing, easy to make mistakes that are very hard to debug. So we're going to introduce a way of getting around this shortly. I'll give you a little hint. There's another construct in Python called a raw string, which changes the way special characters are interpreted and makes all this much easier. So we'll see that shortly. Okay. When we have grouping characters and strings in regular expressions, I mentioned before that one thing I can do is I can make references across the pattern matching, the pattern I'm matching, to say this subpattern and this subpattern must match in exactly the same way. To do that, I need some more backslashes. These are called back reference backslashes. So let's take a look at this. Here's my target string, Paris, Paris in the spring. My search expression is grouped, is a backslash b, which you recall is a word boundary, so beginning of word, followed by one or more word characters, followed by one or more spaces, followed by a backslash backslash 1. Now that backslash backslash 1 in the Python string is really backslash 1 to the pattern matching engine. And backslash 1 is a back reference. It says, whatever comes here needs to be the same as what you found in the first grouping. So the first grouping is this first parentheses here is going to be a bunch of word characters, followed by a bunch of spaces, followed by the same characters. Whatever matched here has to be the same there. Does anybody know what this matches? Anybody want to guess? So it's going to look like two words that are the same separated by a space, one or more spaces. This pattern says find two words that are the same word separated by one or more spaces. And the answer is I will find group 1 is the, and what I'll get then is it will match the. But if I add ignore case, all of a sudden it'll match Paris, Paris. So how useful is this? It's incredibly useful. It's incredibly useful, but it's also bad because of all the backslashes and the numbers. But remember, in a pattern, backslash digit, like 1, 2, 3, 4, 5, refers to the grouping that you have elsewhere in the pattern. Okay. So let's see how we can do. Group 0 is the whole pattern. Group 1 corresponds to the first left parentheses, 2 to the second, and so on. So here is another pattern matching experience. I have any number of A, B, or C's, that's group 1, followed by a D, E, F, followed by the same thing that matched group 2. Well, what's group 2? Group 1 is that first parentheses. Group 2 is the ABC plus. So I'm looking for something that looks like ABC, any number of ABCs, followed by a DEF, followed by exactly the same characters that were in the first part of the pattern. So I'm going to get something that looks almost like a, well, not quite. It's going to be like one part, something in the middle, and the same thing again from the first part. And then I'm going to have an HIJ, followed by pattern 1, which whatever was in that first expression, the same. So here I have AB, DEF, AB, that matches that number 1 grouping. HIJ, and then I have exactly the same thing, and this should match. Notice how I can constrain what the match is by using back references to named parts of the pattern. So that matches. Group 1 will be AB, DEF, AB. Group 2 is just AB. So group 2, left parentheses 1, left parentheses 2 is that ABC plus. So that's group 2. That's going to be AB. Group 1 is that plus DEF plus a reference to group 2. So AB, DEF, AB. And the whole pattern is that substring with an HIJ and then that substring repeated again. And that's why I get a match. Yes?
Is this how, in looking through text,
Sorry, I can't.
is using this grouping how you can sort of distinguish like character names for people in the story?
So we can use regular expressions to great benefit in parsing a novel, say, right? I could write a regular expression to find a name, which we know is like an uppercase word that appears somewhere in the story, presumably not just in the first location of a sentence, right? We can even use this to recognize, for example, patterns like Mr. So-and-so, or Professor so-and-so, or Mrs. so-and-so by looking for the two uppercase words that appear consecutively, not necessarily only at the beginning of a sentence, and sometimes appear independently. So the second word would appear independently, presumably sometimes. So yeah, we can use regular expressions in a big way to help find, to help parse the story, which is what you're going to do in homework 3, in part. Not very complicated stuff. All right, so let's review. We've seen the grouping elements, parentheses. We've seen how we number those groups, and we see how those groups can then be extracted from the match and can even be used to constrain the rest of the match. But sometimes a group is just a group. It's just something you want to have a star after or a plus after, or something where you want to combine pattern elements, but you don't really care how it matches. If that's the case, it is sometimes easier to reduce the amount of counting by just using non-grouping, non-capturing groups. So there's a special character combination, left parentheses, question mark, colon, and right parentheses. This is just like a regular grouping. The only difference is this one isn't counted. It doesn't get an index, and it can't be used as a back reference. So the kinds of groupings we used initially, just A, B star, really should probably be non-capturing groups if you're careful. Reduces the load on the pattern matching engine, and because you're not going to reuse it as a back reference, and you don't need to extract it from the pattern, just match it. Just use that to group elements together for to be able to express repetition of those elements. So here, I have a non-capturing group of ABCs and another non-capturing groups of ABCs inside a capturing group with a DEF in between them, followed by an HIJ and a repetition. How is this different from the one before? Well, because these are non-capturing groups, there's no attempt to make this one match that one. And in fact, ABDEFC is a match because it's any number of ABCs over there and any number of ABCs over here. So I've got the AB and the C separated by DEF. So I have ABDEFC is the first part, followed by HIJ. And then since this first outer group is a capturing group, the back reference refers to the whole pattern and have a repeat of the ABDEFC. All right, so this is a way to write patterns that sort of reduces the load of having all these capturing groups when you don't really need to use the back reference. So my group 0 is the whole match. Group 1 is that first subpattern, and I don't have any way of getting the other. Okay. One last thing to do before we go today, which will make your life a little bit easier. Backslashes are a pain in the neck. And if we use raw strings, we don't have to worry about backslashes. So we've seen a lot of different string characters. We've seen single quotes, we've seen double quotes, we've even seen triple quotes that allow for multi-line strings. Here, we're going to use our quote and quote to enclose strings that are so-called raw strings. A raw string doesn't have any backslashes that are special characters. A backslash in a raw string is just a backslash. So when I'm specifying patterns for regular expressions in particular, the use of raw strings gets me out of all that mess of having to remember that I need a backslash so that the Python string mechanism doesn't read this wrong, and then I need a backslash for the pattern mechanism, which means I have to replicate the backslashes. When you're specifying a pattern, the use of raw strings makes your life much, much easier. And in fact, in general, in programming, if you're not going to have tabs or spaces or new lines that you need to specify in the string, raw strings can be useful elsewhere as well. So here's my original Paris in the spring. Notice that there are no duplicated backslashes in the raw string. I just have a grouping that says start of word, bunch of word characters, followed by any number of strings, followed by a repeated word. And this works just like the other one.
We need to hold an exam after this.
Well, as soon as we're done, 10:20. Class runs till 10:20. So we're almost done. Anyway, so first group is the, and if I ignore case, the first group will be Paris. So remember to use raw strings when you're doing extractions, and when you're dealing with patterns with backslashes, raw strings will save you a lot of trouble. All right, so I've been told it's end of class. It's 10:20 on the dot, so we'll stop now. Question of the day is released right after class.